A supernova is one of the most powerful and awe-inspiring events in the universe, representing both the death and rebirth of stars. To truly understand what a supernova is, it's important to grasp the life cycle of stars and the forces at play within the cosmos. Stars are formed from vast clouds of gas and dust, predominantly hydrogen and helium, and these clouds collapse under the force of gravity. As the material within these clouds condenses, it heats up, igniting nuclear fusion in the star's core. This fusion process converts hydrogen into helium, releasing enormous amounts of energy in the form of light and heat, which allows the star to shine. Throughout most of its life, a star is in a state of equilibrium between the inward pull of gravity and the outward pressure created by the energy from nuclear fusion. This delicate balance is maintained until the star exhausts its nuclear fuel. The point at which the star runs out of fuel marks the beginning of its end, a cataclysmic event that can result in a supernova. A supernova is triggered when a star reaches the end of its life cycle and undergoes a sudden and dramatic explosion. There are two primary types of supernovae, Type 1 and Type 2, each distinguished by the processes that lead to their formation. Type 1 supernovae occur in binary star systems, where two stars orbit each other. One of the stars, usually a white dwarf, accretes material from its companion star, gradually growing in mass. If the white dwarf exceeds a critical mass known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, the star becomes unstable and triggers a runaway thermonuclear reaction, causing it to explode in a supernova. Type 2 supernovae, on the other hand, occur in single massive stars, typically at least 8 times the mass of the Sun. These stars undergo core collapse when they run out of nuclear fuel. The star's core can no longer support the weight of its outer layers, which results in a violent implosion, followed by a tremendous explosion that sends shockwaves and stellar material into space. The energy released by a supernova is staggering. For a brief moment, the exploding star can outshine an entire galaxy, radiating more energy in a few weeks than our Sun will produce over its entire lifetime. Supernovae play a crucial role in the universe, as they are responsible for distributing elements like carbon, oxygen, and iron, which are essential for life, into the interstellar medium. In fact, much of the material that makes up our planet, and even our own bodies, was once forged in the heart of a star that ended its life in a supernova explosion billions of years ago. These explosions are the universe's way of recycling matter, as the elements created in the cores of stars are scattered across space, eventually becoming part of new stars, planets, and even living organisms. This cosmic cycle of creation and destruction is an integral part of the evolution of galaxies and the cosmos as a whole. One of the most famous supernovae observed by humans was SN 1054, which was visible in the year 1054 AD and resulted in the formation of the Crab Nebula. Historical records show that it was so bright that it was visible during the day for several weeks. The remnants of the explosion, known as a supernova remnant, continue to expand outward, creating complex structures of gas and dust. These remnants are often visible in various wavelengths of light, from radio waves to X-rays, allowing astronomers to study the properties of supernovae long after the initial explosion has occurred. Another well-known supernova is SN 1987A, which was discovered in 1987 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This event provided astronomers with invaluable data about the mechanisms behind supernova explosions, as it was the first time that neutrinos, ghostly subatomic particles produced in the core of a collapsing star, were detected in association with a supernova. The study of supernovae has led to significant advancements in our understanding of astrophysics. One of the most important discoveries related to supernovae is their role in measuring cosmic distances. Type I supernovae, which occur in binary systems, are considered standard candles, because their intrinsic brightness is relatively uniform. By comparing the observed brightness of a Type I supernova to its known luminosity, astronomers can determine its distance from Earth. This method has been instrumental in mapping the expansion of the universe and led to the groundbreaking discovery that the universe is not only expanding, but that this expansion is accelerating due to a mysterious force called dark energy. Supernovae are also critical for the formation of neutron stars and black holes. When a massive star undergoes core collapse, the core that remains can form a neutron star, an incredibly dense object composed almost entirely of neutrons. Neutron stars are so dense that a sugar cube-sized amount of their material would weigh as much as a mountain on Earth. In some cases, if the star is massive enough, the core continues to collapse until it forms a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. These exotic objects are some of the most extreme and fascinating phenomena in the universe, and their formation is inextricably linked to the violent deaths of massive stars and supernova explosions. While supernovae are rare events, occurring perhaps once or twice per century in a galaxy like the Milky Way, their effects are profound. The shockwaves generated by supernovae can trigger the formation of new stars by compressing nearby gas clouds, leading to the birth of new stellar generations. The energy released by supernovae can also heat the surrounding interstellar medium, influencing the evolution of galaxies over billions of years. Supernovae are not just dramatic cosmic fireworks. They are fundamental processes that shape the structure and composition of the universe. Recent advancements in technology have allowed astronomers to detect supernovae in distant galaxies, providing a window into the early universe. By studying these distant explosions, scientists can learn more about the conditions that existed in the first few billion years after the Big Bang. Supernovae have become powerful tools for probing the cosmos, helping to answer some of the most profound questions about the nature of the universe, including the origin of elements, the formation of galaxies, and the ultimate fate of the cosmos. As we continue to explore the universe, supernovae remain one of the most captivating and important phenomena in astronomy. They represent the violent deaths of stars but also the beginning of new cycles of cosmic evolution. From creating the elements that make life possible to helping us measure the expansion of the universe, supernovae are a testament to the dynamic and ever-changing nature of the cosmos. Through the light of these distant explosions, we are reminded that we are all part of a vast, interconnected universe, forged from the remnants of stars that exploded billions of years ago. The story of supernovae stretches across cosmic time, intimately tied to the birth and death of stars, the formation of galaxies, and even the very existence of life itself. While their role in the universe is profound, their mysteries run even deeper, prompting scientists to dig further into their mechanisms, effects, and potential consequences for the future of our galaxy and others. To begin with, the life cycle of a star is key to understanding why supernovae happen at all. Stars are essentially nuclear reactors in space, with the core undergoing a process known as nuclear fusion. In the core, hydrogen atoms are smashed together to form helium, releasing immense amounts of energy. This energy radiates outward, creating pressure that counteracts the inward pull of gravity. For the vast majority of a star's life, these two forces remain balanced in what is known as hydrostatic equilibrium. However, as a star ages, it begins to burn through its fuel. Once the core is no longer able to fuse lighter elements into heavier ones, the star faces a crisis. It can no longer generate the energy needed to fight off gravity, and this leads to the catastrophic collapse that can trigger a supernova. Massive stars, those with at least 8 times the mass of the Sun, are the primary candidates for core collapse supernovae, also known as Type II supernovae. As their cores burn through lighter elements, they start to fuse heavier and heavier ones, progressing through elements like carbon, oxygen, and silicon. But the fusion of iron, an element formed in the core of massive stars, signals the end. Fusion involving iron does not release energy. Instead, it consumes energy. When iron builds up in the core, the star is living on borrowed time. Without the outward pressure provided by fusion, gravity takes over. The core collapses in a fraction of a second, creating a shockwave that propagates outward through the star's layers, and this ultimately results in a spectacular explosion, the supernova. What remains after a supernova explosion depends largely on the mass of the star. For many stars, the core that collapses can become a neutron star. These objects are among the densest in the universe, so dense that a neutron star only a few kilometers in diameter can contain the mass of the Sun. The material inside is so tightly packed that electrons and protons merge to form neutrons, giving the star its name. Neutron stars exhibit strange and fascinating properties. For example, some neutron stars become pulsars, which emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, creating a pulsing effect, much like the beam of a lighthouse. Pulsars are critical tools for astronomers studying the extreme physics of dense matter and the behavior of matter under incredible gravitational forces. For the most massive stars, however, even the formation of a neutron star is not enough to halt the collapse of the core. Instead, these stars may continue collapsing into black holes, regions of space where gravity is so intense that not even light can escape. Black holes represent the ultimate consequence of a supernova, a point where the laws of physics as we understand them begin to break down. While supernovae are rare events in our galaxy, the remnants they leave behind, whether neutron stars or black holes, continue to influence the cosmos for millions or even billions of years. Supernova remnants themselves are fascinating objects. When a supernova explodes, it sends shockwaves into the surrounding space, heating up the gas and dust and creating beautiful, intricate structures. These remnants glow in various wavelengths, from visible light to X-rays and radio waves, providing astronomers with detailed information about the explosion and the material ejected from the star. The Crab Nebula, for example, is the remnant of a supernova observed in 1054 AD, and it remains one of the most studied objects in the sky. The filaments of gas and dust visible in the nebula tell a story of a massive explosion that scattered the elements forged in the star's core across the cosmos. Supernovae are not just destructive forces, they are also creators. The heavy elements synthesized in the core of the star during its lifetime and during the supernova explosion itself are spread throughout space, enriching the interstellar medium. These elements, carbon, nitrogen, oxygen, iron, are the building blocks of planets, moons, and even life. Without supernovae, the universe would be a far less interesting place. Life on Earth, and indeed the Earth itself, owes its existence to stars that exploded billions of years ago, seeding the galaxy with the materials necessary for the formation of rocky planets and organic life forms. The cycle of star birth, death, and rebirth is a fundamental aspect of the universe's evolution. When supernovae explode, the shockwaves can trigger the collapse of nearby gas clouds, leading to the formation of new stars. This is another way in which supernovae shape the cosmos. The elements produced in supernovae are incorporated into new generations of stars, planets, and even living organisms. The universe is a recycling machine, with stars forming, exploding, and distributing their material, only for that material to be reused in the formation of new stars and planetary systems. This cosmic cycle of destruction and creation is responsible for the incredible diversity of objects we see in the universe today. In more recent times, astronomers have begun to focus on distant supernovae as a way to study the expansion of the universe. Type I supernovae, in particular, have proven to be invaluable tools for measuring cosmic distances. These supernovae are believed to occur in binary star systems where a white dwarf accretes matter from its companion star. Once the white dwarf reaches a critical mass, it undergoes a runaway nuclear reaction and explodes as a supernova. Because Type I supernovae have a consistent luminosity, they are used as standard candles to measure the distances to galaxies. By comparing the observed brightness of a Type I supernova with its intrinsic brightness, astronomers can calculate how far away it is. This method of using supernovae to measure distances has led to one of the most astonishing discoveries in modern astrophysics: the acceleration of the universe's expansion. In the late 1990s, teams of astronomers studying distant Type I supernovae made the surprising discovery that these supernovae appeared dimmer than expected, implying that they were farther away than predicted. This observation led to the conclusion that the universe's expansion is not slowing down, as once thought, but is actually speeding up. The cause of this accelerated expansion is a mysterious force known as dark energy, which remains one of the greatest unsolved puzzles in cosmology. The discovery of dark energy has revolutionized our understanding of the universe and has raised profound questions about the ultimate fate of the cosmos. If the expansion of the universe continues to accelerate, it could lead to a future in which galaxies drift farther and farther apart, eventually becoming isolated in a dark, empty universe. The role of supernovae in this process is vital, as they provide the observational evidence needed to understand the dynamics of the cosmos. In this sense, supernovae are not just spectacular events, they are cosmic beacons that illuminate the farthest reaches of space and time, giving us insight into the nature of the universe itself. Despite all that we have learned from supernovae, there is still much that remains unknown. For example, astronomers are still trying to understand the precise mechanisms that trigger supernova explosions. While core collapse supernovae are generally well understood, the details of the explosion process, how the shockwave propagates through the star and how much energy is released, are still the subject of active research. Similarly, while Type Ia supernovae are used as standard candles, there are still questions about the exact conditions that lead to these explosions. Are all Type Ia supernovae truly identical, or are there subtle variations that could affect our measurements of cosmic distances? In addition to these questions, astronomers are also searching for supernovae in different environments, including distant galaxies and the early universe. Studying supernovae in these contexts could provide valuable information about the history of star formation and the evolution of galaxies. Supernovae are also being studied as potential sources of gravitational waves, ripples in space-time caused by the acceleration of massive objects. Detecting gravitational waves from supernovae could open up a new way of studying these powerful explosions and provide insight into the physics of core collapse. Looking to the future, the continued study of supernovae promises to yield even more discoveries about the nature of the universe. As telescopes become more powerful and sensitive, astronomers will be able to detect supernovae in ever more distant galaxies, pushing the boundaries of our understanding of the cosmos. Moreover, supernovae are likely to play a key role in the search for extraterrestrial life. The elements created in supernovae, carbon, oxygen, nitrogen, and more, are essential for life as we know it. By studying how these elements are distributed throughout the galaxy, we may be able to identify regions of space where conditions are favorable for the development of life. Supernovae have shaped the universe in ways that we are only beginning to understand. They are both destroyers and creators, tearing apart stars while sowing the seeds for new generations of celestial bodies. Through their light, we have glimpsed the most distant reaches of space and the farthest corners of time. They are the universe's great fireworks, marking the end of one star's journey and the beginning of another. As we continue to study these cosmic titans, we are reminded of our own connection to the stars and the vast, ever-changing universe that we call home. The cosmic role of supernovae stretches far beyond what we can observe with our telescopes. As one of the most energetic events in the universe, their influence transcends the local environments of galaxies, affecting everything from galactic evolution to the potential for life on distant planets. Despite being short-lived in terms of cosmological time, supernovae create long-lasting effects that ripple throughout the universe, making them not just dramatic endpoints in the life of stars but critical agents of cosmic transformation. One of the most intriguing questions about supernovae is their role in the habitable zones of the galaxy, areas where conditions are just right for life as we know it to thrive. This concept, known as the galactic habitable zone, is analogous to the circumstellar habitable zones around stars, where a planet might have the right conditions for liquid water. In the broader context of a galaxy, such a zone depends not only on the distance from the galactic center but also on the frequency and location of supernova explosions. Supernovae release intense radiation and particles, known as cosmic rays, which can have a profound impact on planets within their vicinity. A nearby supernova could strip a planet's atmosphere, bombard it with high-energy radiation, or even trigger mass extinctions, as some scientists hypothesize may have happened on Earth during past extinction events. However, the relationship between supernovae and life is not purely destructive. These explosions are also essential for enriching planets with the elements necessary for life. Carbon, nitrogen, oxygen, and many of the other building blocks of life are produced in the hearts of stars and distributed throughout the galaxy by supernova explosions. Without these elements, the formation of planets and the complex chemistry that leads to life would be impossible. In this way, supernovae act as cosmic gardeners, fertilizing the universe with the materials needed for life to bloom. The interplay between supernovae and the potential for life elsewhere in the galaxy raises fascinating questions about the conditions necessary for civilizations to develop. Could nearby supernovae have a hand in shaping the destiny of alien civilizations, just as they may have shaped the evolution of life on Earth? Some astrobiologists speculate that the timing and frequency of supernova explosions could influence the development of intelligent life. In regions of the galaxy where supernovae are too frequent, the radiation might sterilize planets before life has a chance to evolve. In more stable regions, where supernovae occur less often but still provide the necessary elements for planet formation, life might have the time and resources to flourish. In the broader context of the universe, supernovae also play a critical role in shaping the evolution of galaxies themselves. Galaxies are not static objects. They are dynamic, ever-changing systems shaped by internal and external forces. Supernova explosions contribute to this dynamic environment by driving massive amounts of energy and material into the interstellar medium. These stellar explosions can trigger star formation by compressing gas clouds, but they can also disrupt star formation by heating up and dispersing gas, preventing it from condensing into new stars. This dual role, both promoting and hindering star formation, makes supernovae essential players in the ongoing process of galactic evolution. Moreover, supernovae contribute to the chemical evolution of galaxies, a process known as galactic nucleosynthesis. As stars undergo fusion throughout their lifetimes, they create heavier elements in their cores. When these stars explode as supernovae, they scatter these elements throughout the galaxy, enriching the interstellar medium with metals. In astronomy, metals refers to all elements heavier than hydrogen and helium. This gradual enrichment over billions of years has led to the diversity of chemical compositions we observe in stars and planets today. In this way, supernovae act as cosmic alchemists, transforming light elements into the heavier ones that make rocky planets and life possible. One of the most intriguing aspects of supernovae in recent years has been the search for their remnants in the form of black holes. As we mentioned earlier, supernova explosions of very massive stars can leave behind a black hole. These objects, formed from the gravitational collapse of a massive star's core, represent some of the most extreme environments in the universe. Studying these black holes, particularly through the detection of gravitational waves, ripples in space-time caused by violent cosmic events like supernovae, has opened up an entirely new field of astrophysics. Gravitational wave observatories, such as LIGO and Virgo, have already detected waves produced by the collisions of black holes, and researchers are now focusing on the signals that might be produced during the collapse of a massive star into a black hole. These observations could offer unprecedented insights into the physics of core collapse supernovae and the formation of black holes. The detection of gravitational waves from supernovae could also help solve long-standing questions about the exact mechanisms of core collapse and how black holes form from these catastrophic events. In addition to black holes, some supernova remnants are theorized to give rise to even more exotic objects, magnetars. Magnetars are a type of neutron star with incredibly strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields can cause massive starquakes on the surface of the magnetar, releasing bursts of gamma rays and X-rays that can be detected from Earth. While rare, these magnetar outbursts offer a glimpse into the extreme physics of matter under conditions that we cannot replicate in laboratories on Earth. Understanding how supernovae give rise to magnetars and the dynamics of their powerful magnetic fields remains a subject of active research. As our observational capabilities continue to improve, particularly with the launch of new space telescopes and the advancement of ground-based observatories, our understanding of supernovae is poised to deepen even further. For example, the James Webb Space Telescope, JWST, launched in December 2021, is expected to play a critical role in observing the earliest supernovae that occurred in the universe. These ancient explosions, which occurred when the universe was just a few 100 million years old, hold the key to understanding how the first stars and galaxies formed. By studying the light from these distant supernovae, scientists hope to unravel the mysteries of the early universe and the conditions that gave rise to the cosmos as we know it. Looking even further ahead, supernovae may play a role in the search for extraterrestrial intelligence. SETI. One of the key challenges in the search for alien civilizations is identifying signals that could indicate the presence of intelligent life. Some researchers have speculated that supernovae could serve as natural markers in this search. If an advanced civilization were capable of harnessing the energy of a supernova or using the event as a means of communication, the resulting signals could be detectable by our current or future technology. While this idea remains speculative, it underscores the potential of supernovae to serve as cosmic signposts, guiding us in our search for life beyond Earth. In our own galaxy, the Milky Way, the potential for future supernovae remains a topic of great interest. One of the most closely watched stars in our galaxy is Betelgeuse, a red supergiant in the constellation Orion. Betelgeuse is nearing the end of its life and is expected to explode as a Type II supernova sometime within the next 100,000 years, a blink of an eye in cosmic terms. When it does, it will be a spectacular event, visible from Earth even in daylight. While the exact timing of Betelgeuse's explosion is uncertain, its impending fate offers a unique opportunity to study a supernova in our cosmic backyard. When Betelgeuse finally explodes, it will provide astronomers with a front-row seat to one of the most powerful events in the universe. The possibility of witnessing a nearby supernova, particularly one as close as Betelgeuse, raises important questions about the effects such an event could have on Earth. While Betelgeuse is far enough away that its explosion would not pose a direct threat to our planet, a closer supernova could have serious consequences. If a supernova occurred within a few tens of light years from Earth, the resulting radiation could strip away the ozone layer, leaving the planet vulnerable to harmful ultraviolet radiation from the Sun. Some scientists have hypothesized that supernovae could have played a role in past mass extinction events on Earth, though this remains a subject of debate. Despite the potential risks, supernovae are not only a source of scientific fascination but also a reminder of the interconnectedness of the universe. The elements forged in the heart of dying stars are the same elements that make up our bodies, our planet, and everything around us. Supernovae are a testament to the cycles of creation and destruction that govern the cosmos, where even in death, stars give rise to new life. As we continue to study these cosmic explosions, we gain not only a deeper understanding of the universe but also a greater appreciation for our place within it. In the grand scheme of things, the supernova is a fleeting event, a brief, albeit spectacular, moment in the life of a star. But its impact resonates across space and time, shaping galaxies, influencing the potential for life, and offering insights into the most fundamental questions about the nature of the universe. Supernovae are a reminder that the cosmos is constantly evolving, driven by forces both seen and unseen. Through the study of these incredible explosions, we come closer to understanding the universe's most profound mysteries, from the origins of matter to the ultimate fate of the stars themselves. The exploration of supernovae also connects us to one of the biggest mysteries in astrophysics, dark energy, and the expansion of the universe. The discovery of the accelerating expansion of the universe in the late 1990s, which earned the Nobel Prize in Physics, relied heavily on the study of Type Ia supernovae. These particular supernovae, formed from the thermonuclear explosion of a white dwarf in a binary system, have been used as standard candles to measure cosmic distances. Because they explode with a consistent intrinsic brightness, they provide an invaluable tool for determining how far away galaxies are. By observing distant Type Ia supernovae, astronomers were able to determine that the expansion of the universe is accelerating, a discovery that led to the hypothesis of dark energy, a mysterious force that makes up about 70% of the universe's total energy content and is pushing galaxies apart at an ever-increasing rate. Without the study of supernovae, this critical insight into the nature of the cosmos might not have been possible. The connection between supernovae and dark energy highlights how these cataclysmic events are not just important for understanding stellar evolution, but are also central to our comprehension of the universe as a whole. This discovery raised profound questions about the fate of the universe. If dark energy continues to dominate, the universe may continue to expand forever, growing colder and darker as galaxies drift farther apart and stars burn out. In this scenario, supernovae, Once the brilliant beacons that illuminated the cosmic landscape would become rare and eventually cease altogether, as the fuel necessary for star formation runs out. This heat death of the universe is one of the more somber possibilities for the ultimate fate of everything, where even the most spectacular of cosmic events, like supernovae, would fade into oblivion. Yet, despite this grim future, supernovae represent moments of profound beauty and transformation. They are the cosmic engines that create the heavy elements, drive the evolution of galaxies, and provide us with a glimpse into the most fundamental forces of nature. Their study has led to groundbreaking discoveries in physics and astronomy, and they continue to be at the forefront of some of the most exciting research in science. One of the most pressing challenges in the study of supernovae is predicting when and where they will occur. While we understand the broad circumstances that lead to a supernova, whether it be the collapse of a massive star's core or the runaway thermonuclear reaction of a white dwarf, pinpointing the exact moment of explosion remains elusive. However, advances in observational technology and data analysis are bringing us closer to being able to predict supernovae in real time. For example, astronomers have recently observed a red supergiant in the process of exploding as a supernova, catching the event in its early stages before the star's outer layers were ejected. This kind of observation offers unprecedented insight into the pre-explosion conditions of stars and could eventually help us predict when other nearby stars might go supernova. Another fascinating area of study is the potential for supernova-triggered gamma-ray bursts, GRBs, which are among the most energetic events in the universe. GRBs are brief but incredibly intense emissions of gamma rays, and some are thought to be linked to supernovae, particularly those involving massive stars collapsing into black holes. These long-duration GRBs can last anywhere from a few seconds to several minutes and release as much energy as the Sun will in its entire 10 billion-year lifetime. Although GRBs are rare, their immense power makes them important objects of study, particularly for understanding extreme astrophysical processes. There's also the prospect of supernovae and their remnants offering clues to the mysteries of particle physics. Neutrinos, nearly massless subatomic particles, are produced in vast quantities during a supernova explosion. These elusive particles interact very weakly with matter, making them incredibly difficult to detect, but they offer a unique window into the processes happening deep within an exploding star. The detection of neutrinos from supernova 1987A, a star that exploded in the Large Magellanic Cloud in 1987, was a landmark achievement in astrophysics and provided valuable insights into the mechanisms of core-collapse supernovae. Future supernovae could help physicists better understand the behavior of neutrinos and their role in the universe. Even the remnants of supernovae, the neutron stars, pulsars, black holes, and supernova remnants, SNRs, that are left behind, continue to be objects of fascination and research. These remnants serve as laboratories for studying matter under extreme conditions. Neutron stars, for example, pack more mass than the Sun into a sphere only about 20 kilometers in diameter, creating an environment of unimaginable density. The behavior of matter at such densities is not fully understood, and neutron stars provide a unique testing ground for theories of quantum physics and general relativity. Supernova remnants, the expanding clouds of gas and dust left behind after a supernova explosion, are also important for studying the processes of chemical enrichment and star formation. These remnants can create stunning nebulae, such as the Crab Nebula, which is the remnant of a supernova observed by Chinese astronomers in 1054 AD. Supernova remnants are often studied across multiple wavelengths of light, from radio waves to X-rays, giving astronomers a detailed picture of the physical conditions in these fascinating objects. In addition, the study of supernovae offers insights into the early universe, providing clues about the first generation of stars, known as population 3 stars. These primordial stars were composed almost entirely of hydrogen and helium, the light elements created in the Big Bang, and they are believed to have been massive, short-lived, and prone to exploding as supernovae. While no population 3 stars have been directly observed, their existence is inferred from the patterns of elements in ancient stars. Understanding how these early supernovae enriched the interstellar medium with heavier elements is crucial for piecing together the history of the cosmos and the formation of galaxies. As we delve deeper into the study of supernovae, we also encounter the philosophical and existential questions that naturally arise when contemplating the cosmos. Supernovae are a reminder of the immense scale of time and space, and of the impermanence of even the most seemingly eternal objects in the sky. They are a testament to the cycle of birth, death, and rebirth that governs the universe, where the death of one star leads to the formation of new stars and planets, and perhaps even life. In many ways, supernovae also challenge our sense of human significance. The forces at play in these explosions are so far beyond our everyday experience that they can make our own concerns seem trivial by comparison. And yet, at the same time, the elements created in these stellar explosions are what make life, including human life, possible. We are, quite literally, made of star stuff, forged in the hearts of long-dead stars and scattered across the cosmos by supernovae. The study of supernovae also connects us to the future, both of our own planet and of the universe as a whole. While the Sun is not massive enough to end its life as a supernova, it will eventually exhaust its nuclear fuel and evolve into a red giant, shedding its outer layers and leaving behind a white dwarf. In the distant future, long after the Sun has faded, the universe may continue to witness supernova explosions, marking the deaths of stars in far-off galaxies. But as the universe expands and the formation of new stars slows down, supernovae themselves will become increasingly rare. Eventually, the universe may reach a point where no new stars form and no new supernovae occur, a cold, dark, and quiet universe, where the brilliant explosions of dying stars are but a distant memory. Yet even in this distant future, the legacy of supernovae will live on, encoded in the elements that make up planets, stars, and even life itself. They are the cosmic beacons that illuminate the universe's past, present, and future, offering a glimpse into the profound forces that shape the cosmos. And as we continue to study these extraordinary events, we not only learn more about the universe, but we also gain a deeper appreciation for the delicate and interconnected web of processes that make our existence possible. Supernovae are more than just the violent deaths of stars. They are the harbingers of creation, the forgers of elements, and the illuminators of the universe. They are the explosions that give birth to new worlds and new possibilities, reminding us that even in the face of cosmic destruction, the seeds of life and creation are sown. As we continue to unravel the mysteries of supernovae, we gain a deeper understanding of their profound significance in the grand tapestry of the universe. These colossal explosions are not isolated events but rather essential processes that connect the microscopic with the macroscopic, the individual star with the broader cosmic structure, and the immediate with the eternal. Supernovae are the moments where time, space, and energy converge, releasing forces so powerful they reshape not only their immediate surroundings but also the distant future of galaxies and star systems. One of the most awe-inspiring aspects of supernovae is their role in the genesis of complex life. Without supernovae, the universe would be devoid of the heavier elements necessary for the formation of planets, atmospheres, and living organisms. Every atom of oxygen, carbon, iron, and nitrogen, the essential building blocks of life as we know it, was forged in the furnace of a star and ejected into space by a supernova. In this sense, the story of supernovae is not just a story of stellar death but of cosmic renewal, of the cycles that give rise to life. In a universe without supernovae, there would be no Earth, no oceans, no atmosphere to breathe, and no sentient beings to observe and reflect on these celestial events. The legacy of supernovae is embedded in the very atoms of our bodies, in the iron that courses through our blood and the calcium that strengthens our bones. When we look up at the night sky and ponder the stars, we are, in a way, reflecting on our own origins. We are star children, born from the ashes of long-dead stars, and supernovae are our distant ancestors. This realization has a profound impact on our understanding of life and the cosmos. It challenges us to see life not as something that exists in isolation but as part of a much larger and interconnected system. The life cycle of stars and the formation of elements are intimately linked to the conditions necessary for life to arise. Supernovae, in their moment of destruction, sow the seeds for future generations of stars, planets, and possibly life forms. This cyclical nature of creation and destruction is a recurring theme throughout the universe, and it resonates with many philosophical and spiritual traditions that emphasize the unity of all things. At the same time, the sheer scale of supernovae and their impact on the universe can make us feel insignificant. The forces involved are so immense, the distance is so vast, and the timescales so long that our human concerns seem almost inconsequential in comparison. A single supernova can outshine an entire galaxy for a brief moment, and the remnants of that explosion can persist for millions or even billions of years. In contrast, the entire span of human civilization is but a blink of an eye in cosmic terms. Yet, even in the face of this cosmic vastness, we find meaning in our connection to the stars. Supernovae remind us that we are part of something far greater than ourselves, something that stretches across time and space and binds all of existence together. The atoms in our bodies, the air we breathe, and the planet we call home are all part of a cosmic dance that has been unfolding for billions of years. And in that dance, supernovae play a central role, acting as both the destroyers and creators of worlds. The study of supernovae also pushes the boundaries of human knowledge and technological achievement. Observing and understanding these distant explosions requires cutting-edge instruments and technologies, from powerful telescopes that can detect faint light from the farthest reaches of the universe to neutrino detectors that capture the elusive particles emitted during a supernova's core collapse. Each new supernova observed provides valuable data that helps scientists refine their models of stellar evolution, test the limits of physics, and probe the fundamental forces that govern the cosmos. In recent years, the advent of large-scale sky surveys and advanced computer simulations has revolutionized our ability to study supernovae. Projects like the Large Synoptic Survey Telescope, LSST, and the upcoming James Webb Space Telescope, JWST, promise to provide unprecedented insights into the nature of supernovae and their role in the evolution of the universe. These instruments will allow astronomers to observe supernovae in real time, study their afterglows in detail, and even look back in time to see the first supernovae that lit up the early universe. One of the most exciting prospects for the future of supernova research is the potential to detect supernovae in other galaxies that are billions of light years away. By observing these ancient explosions, we can learn more about the conditions that existed in the early universe and gain insight into how galaxies, stars, and planetary systems formed and evolved over time. These distant supernovae serve as cosmic time capsules, preserving information about the state of the universe billions of years ago. Furthermore, the study of supernovae is increasingly intertwined with the search for extraterrestrial life. Supernovae can have both positive and negative effects on the habitability of planets. On the one hand, the elements ejected by supernovae are necessary for the formation of planets and the development of life. On the other hand, the intense radiation and shockwaves from a nearby supernova could potentially sterilize planets and wipe out any existing life forms. Understanding the balance between these effects is crucial for determining where and when life might emerge in the universe. The impact of a supernova on nearby planetary systems is a topic of much debate and speculation. While a supernova occurring too close to a planet could be catastrophic, the shockwaves and radiation from more distant supernovae might actually trigger the formation of new stars and planetary systems by compressing gas clouds in interstellar space. These opposing effects highlight the complex and dynamic nature of the universe, where destruction often leads to creation, and the most violent events can give rise to new beginnings. Supernovae also hold a special place in the search for advanced extraterrestrial civilizations. Some scientists have speculated that a sufficiently advanced civilization might be able to harness the energy of a supernova for technological purposes, or even trigger a supernova intentionally as a means of communication or defense. While these ideas remain speculative, they reflect the immense power of supernovae and the tantalizing possibilities they offer for future exploration. In our quest to understand supernovae, we are constantly reminded of the vastness and mystery of the universe. Each new discovery brings with it new questions, new challenges, and new opportunities for exploration. Supernovae, in all their brilliance and destructiveness, represent the ultimate frontier of astrophysics, a place where our understanding of the universe is tested and expanded, where the laws of physics are pushed to their limits, and where the fundamental nature of reality itself is revealed. As we look to the future, the study of supernovae will undoubtedly continue to play a central role in our quest to understand the universe. They are not only key to understanding the life cycles of stars but also to unlocking the deepest secrets of the cosmos, from the nature of dark energy to the formation of galaxies and the possibility of life beyond Earth. Supernovae are cosmic events of unparalleled significance. They are the explosive deaths of stars, the creators of elements, the engines of galaxy evolution, and the harbingers of cosmic mysteries yet to be solved. Their study bridges the gap between the vast and the minute, between the distant reaches of the universe and the very atoms that make up our bodies. In contemplating supernovae, we are not just observing the end of stars, but the beginnings of worlds, the cycles of life and death, and the eternal dance of matter and energy that defines the universe itself. The brilliance of a supernova may be fleeting, but its impact resonates through time and space, shaping the universe and reminding us of our own place within the cosmos. The journey to understanding supernovae is far from complete. As with many other phenomena in the cosmos, the more we uncover, the more questions arise. Supernovae push the boundaries of our knowledge and understanding of astrophysics, not only challenging our grasp of the physical laws governing the universe but also compelling us to rethink the nature of existence itself. With every discovery, we edge closer to comprehending the mechanisms that power these spectacular explosions, yet the mysteries they pose remain as deep and enigmatic as ever. For instance, while we have classified supernovae into different types based on their origins and characteristics, Type I, Type II, and their subcategories, there is still much debate about the finer details of how these stars explode. What triggers a white dwarf to accumulate just enough mass to ignite a Type I supernova? What determines whether a massive star will collapse into a neutron star or a black hole? The precise conditions that lead to these outcomes remain the subject of ongoing research, with astrophysicists running complex simulations to model the inner workings of stars as they evolve toward their explosive deaths. In recent years, advancements in computer modeling have allowed scientists to simulate the internal dynamics of massive stars in greater detail than ever before. By running these simulations, researchers can test various hypotheses about the processes that occur in the final moments before a supernova. However, even the most sophisticated models are limited by the complexity of the physics involved. Stars are not simple spheres of gas but dynamic systems with layers of different elements, magnetic fields, rotation, and turbulence, all of which affect how they evolve and ultimately explode. One of the most intriguing aspects of supernova research is the study of the exotic remnants they leave behind. When a massive star explodes, its core may collapse into an incredibly dense object, either a neutron star or a black hole. Neutron stars, as the name suggests, are composed almost entirely of neutrons and are so dense that a sugar cube-sized amount of neutron star material would weigh as much as Mount Everest. Black holes, on the other hand, represent the ultimate endpoint of stellar collapse, regions of space where gravity is so intense that not even light can escape. These remnants are among the most extreme objects in the universe, and their study provides insight into the fundamental nature of matter and space-time. Neutron stars, particularly pulsars, a type of rapidly rotating neutron star, are of particular interest to astronomers. These remnants emit beams of electromagnetic radiation, often in the form of radio waves, that can be detected by radio telescopes. As a pulsar rotates, its beams sweep across the sky like a lighthouse, producing a periodic signal that can be measured with incredible precision. Some pulsars are so stable that they act as natural clocks, providing a way to test theories of gravity and relativity under extreme conditions. The study of pulsars has led to important discoveries, such as the indirect detection of gravitational waves and insights into the behavior of matter at nuclear densities. Black holes, the more enigmatic remnants of supernovae, pose some of the most profound questions in modern physics. While their existence is widely accepted, the details of what happens inside a black hole remain a mystery. The boundary of a black hole, known as the event horizon, marks the point of no return. Once something crosses this threshold, it is swallowed by the black hole and cannot escape. Inside the event horizon, according to current theories, the laws of physics as we understand them break down, and space-time itself is distorted beyond recognition. The study of black holes, particularly through the detection of gravitational waves from merging black holes, has opened a new window into these mysterious objects and the nature of gravity. Supernovae also play a critical role in understanding the evolution of galaxies. Galaxies are not static collections of stars but dynamic systems that evolve over billions of years. Supernovae are essential drivers of this evolution, injecting energy and heavy elements into the interstellar medium. This process, known as supernova feedback, regulates star formation and shapes the structure of galaxies. Without supernovae, galaxies would look very different, more compact, with fewer heavy elements and a less complex structure. In dwarf galaxies, which are smaller and less massive than spiral galaxies like the Milky Way, supernovae can have an even more pronounced effect. A single supernova explosion can blow away much of the gas in a dwarf galaxy, effectively halting star formation for millions of years. These galactic winds, driven by the energy of supernova explosions, help to explain why dwarf galaxies often have low levels of star formation and are deficient in heavy elements. Even in larger galaxies, supernovae contribute to the formation of large-scale structures. The hot, ionized gas ejected by supernovae can form bubbles in the interstellar medium, which expand and eventually merge with other bubbles, creating vast cavities known as superbubbles. These structures can extend for hundreds of light years and have a profound impact on the distribution of gas and stars within galaxies. In some cases, the shockwaves from supernovae can even trigger the formation of new stars by compressing clouds of gas and dust. As our understanding of supernovae continues to deepen, so too does our appreciation for their role in shaping the cosmos. The elements created in supernovae are not just the building blocks of planets and life. They are also essential for the formation of planets themselves. Without the heavy elements produced in supernovae, planets like Earth would not exist, and the complex chemistry necessary for life would be impossible. In this sense, supernovae are responsible not only for the creation of stars and galaxies, but also for the very conditions that make life possible. Looking to the future, the next generation of telescopes and observatories promises to revolutionize our understanding of supernovae. The James Webb Space Telescope, JWST, set to launch soon, will be able to peer deeper into space and time than ever before, allowing astronomers to observe the first supernovae that occurred shortly after the Big Bang. These ancient explosions hold the key to understanding how the first stars and galaxies formed and how the universe evolved in its earliest stages. In addition to the JWST, new ground-based observatories such as the Vera C. Rubin Observatory will conduct massive sky surveys, capturing thousands of supernovae each year. This will provide a wealth of data for astronomers to analyze, helping them to refine their models of stellar evolution and improve our understanding of the different types of supernovae. These observations will also shed light on some of the most pressing questions in cosmology, such as the nature of dark energy and the ultimate fate of the universe. Moreover, the detection of gravitational waves from supernovae and other cataclysmic events is poised to become a major area of research in the coming decades. The first direct detection of gravitational waves in 2015, from the merger of two black holes, opened up a new field of astronomy, and researchers are now working to detect the faint gravitational waves produced by supernovae. These waves carry information about the internal dynamics of exploding stars, providing a unique perspective on the processes that occur during a supernova. As we stand on the cusp of these exciting developments, it's clear that supernovae will continue to be a central focus of astrophysical research for years to come. They are not only the key to understanding the life cycles of stars but also fundamental to our understanding of the universe itself. Supernovae bridge the gap between the very small, the atomic nuclei forged in the heat of an explosion, and the very large, the galaxies and cosmic structures shaped by these events. In many ways, supernovae represent the ultimate expression of the universe's complexity and beauty. They are a reminder of the vast forces at play in the cosmos and of our own connection to the stars. They challenge us to push the boundaries of human knowledge and inspire us to continue exploring the mysteries of the universe. As we peer deeper into space and unravel the secrets of these incredible explosions, we gain not only a deeper understanding of the cosmos but also a greater appreciation for the forces that have shaped our world and our place in the universe. The study of supernovae is far from complete, but with every new discovery, we come closer to answering some of the most profound questions about the nature of reality, the origins of life, and the ultimate fate of the cosmos. Supernovae, in all their brilliance and destructive power, offer us a glimpse into the workings of the universe at its most fundamental level, a universe where destruction leads to creation, where chaos gives rise to order, and where the death of a star can light the way for new beginnings. As we delve further into the study of supernovae, the boundaries of what we know continue to expand, revealing an intricate dance of matter, energy, and time that plays out on cosmic scales. Supernovae are not simply isolated phenomena but are part of a broader web of processes that shape the evolution of galaxies, influence the birth and death of stars, and ultimately dictate the fate of the universe itself. One of the most important roles that supernovae play is in the dispersal of heavy elements across the cosmos. This process, often referred to as nucleosynthesis, is the reason that the universe contains the raw materials necessary for planets, moons, and life as we know it. In the cores of massive stars, nuclear fusion generates lighter elements like hydrogen and helium into progressively heavier elements such as carbon, oxygen, silicon, and iron. However, it is only during the explosive death throes of a supernova that these elements are hurled into space, where they become the building blocks of new stars and planetary systems. This recycling of matter is what gives supernovae their cosmic importance. Without them, the universe would be a much less interesting place, filled with hydrogen and helium, but lacking the rich diversity of elements needed for complex chemistry. Every molecule of water, every grain of sand, every atom in your body owes its existence to the alchemical furnaces inside stars and the explosive release of those elements by supernovae. In this way, supernovae are not only the creators of worlds but the crucibles in which the seeds of life are sown. The remnants of supernovae are equally fascinating. When a star explodes, it often leaves behind an incredibly dense object in its wake. As mentioned before, depending on the mass of the star, this remnant can either be a neutron star or a black hole. Neutron stars, in particular, are one of the most extraordinary objects in the universe. Despite their small size, often only about 20 kilometers in diameter, they pack more mass than the Sun into that tiny space. The density of neutron stars is so extreme that a teaspoon of their material would weigh billions of tons on Earth. Neutron stars also possess incredibly strong magnetic fields, billions of times stronger than any magnetic field produced on Earth. In some cases, these neutron stars are born with rapid rotation, spinning many times per second. As they rotate, beams of radiation shoot out from their magnetic poles, creating pulsars. These pulsars are so precise in their timing that they are often referred to as the universe's natural lighthouses. By studying pulsars, astronomers have made groundbreaking discoveries, such as the indirect detection of gravitational waves and insights into the behavior of matter under extreme conditions. Black holes, the other possible remnants of supernovae, are perhaps even more mysterious. When a supermassive star collapses, its core can be compressed into a singularity, a point where the gravitational pull is so intense that space and time themselves are distorted beyond recognition. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Black holes are a window into the most extreme aspects of general relativity, and their study has profound implications for our understanding of gravity, time, and the nature of the universe. Recent developments in astronomy, particularly the detection of gravitational waves, have opened up new avenues for studying black holes. When black holes collide, they send ripples through the fabric of space-time, which can be detected by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory. These gravitational waves carry information about the masses, spins, and orbits of the black holes involved in the collision, providing insights into how these enigmatic objects form, interact, and merge over time. The discovery of black hole mergers has also raised new questions about the formation of supermassive black holes, those that reside at the centers of galaxies and have masses millions to billions of times that of the Sun. How do these giants form? Do they grow from the mergers of smaller black holes, or do they form directly from the collapse of massive stars in the early universe? These questions are at the forefront of modern astrophysics, and the study of supernovae plays a crucial role in addressing them. Another fascinating aspect of supernovae is their potential connection to gamma-ray bursts, GRBs, the most energetic events in the universe. These bursts release more energy in a few seconds than the Sun will produce over its entire 10 billion-year lifetime. Some gamma-ray bursts are thought to be associated with the collapse of massive stars and hypernovae, extremely powerful supernova explosions. The exact mechanisms that produce gamma-ray bursts remain a topic of intense study, but their association with supernovae highlights the extreme conditions that arise during the death of massive stars. In addition to their role in the dispersal of elements and the creation of neutron stars, black holes, and gamma-ray bursts, supernovae also serve as important tools for understanding the expansion of the universe. Type I supernovae, in particular, are used as standard candles to measure cosmic distances. These supernovae occur in binary star systems where a white dwarf star accretes matter from a companion star until it reaches a critical mass and explodes in a thermonuclear blast. Because Type I supernovae have a consistent intrinsic brightness, astronomers can use them to determine how far away a galaxy is based on how bright the supernova appears from Earth. This method of using Type I supernovae as standard candles has led to one of the most surprising discoveries in modern cosmology: the accelerating expansion of the universe. In the late 1990s, astronomers observing distant supernovae found that they were dimmer than expected, indicating that the universe's expansion is speeding up over time. This discovery led to the proposal of dark energy, a mysterious force that makes up about 70% of the universe and is driving its accelerated expansion. Supernovae, therefore, are not only cosmic explosions but also key players in our understanding of the fundamental structure of the universe. They provide clues about the origins of the elements, the behavior of matter under extreme conditions, and the forces that shape the cosmos on the largest scales. Through their study, we learn about the birth and death of stars, the formation of galaxies, and the ultimate fate of the universe. Looking ahead, the future of supernova research is bright. New telescopes and observatories, both on the ground and in space, will continue to push the boundaries of our knowledge. The James Webb Space Telescope, JWST, will allow us to peer into the early universe and observe the first supernovae that occurred shortly after the Big Bang. Meanwhile, the Vera C. Rubin Observatory will survey the sky in unprecedented detail, capturing thousands of supernovae each year and providing a wealth of data for astronomers to study. In addition, advancements in computer simulations and theoretical models will help scientists better understand the internal dynamics of stars and the processes that lead to supernovae. By simulating the collapse of a star in 3 dimensions, researchers can explore the complex interactions between gravity, nuclear fusion, and the magnetic fields that shape the final moments of a star's life. These simulations will help refine our understanding of how different types of supernovae occur and what determines their outcomes. Furthermore, the continued detection of gravitational waves will provide new insights into the most extreme events in the universe. Gravitational wave observatories like LIGO and Virgo have already detected the mergers of black holes and neutron stars, and future observatories, such as the space-based LISA, Laser Interferometer Space Antenna, will be able to detect gravitational waves from even more distant and massive events, including the collisions of supermassive black holes. As we continue to explore the mysteries of supernovae, we are reminded of the profound interconnectedness of all things in the universe. From the smallest particles to the largest galaxies, the forces that govern the cosmos operate on scales both vast and intimate. Supernovae are a testament to the power of these forces, revealing the beauty and complexity of a universe in constant motion. Their brilliance, though fleeting, leaves an indelible mark on the fabric of space and time, shaping the future of stars, planets, and life itself. In contemplating the wonders of supernovae, we are also reminded of our own place in the cosmos. We, too, are products of this cosmic cycle, born from the remnants of ancient stars and destined to return to the stars in the far future. Supernovae, in their fiery deaths, are not just cosmic spectacles but harbingers of rebirth, renewal, and the eternal cycle of creation and destruction that defines the universe. Through their study, we come to understand not only the mechanics of the cosmos but also our deep connection to the stars and the infinite possibilities that lie beyond the horizon of human knowledge. The significance of supernovae stretches beyond their role in the cosmic recycling of matter or their contribution to the formation of neutron stars and black holes. They also fundamentally alter the structure of galaxies. When supernovae explode, they send shockwaves that ripple through the interstellar medium, the tenuous gas and dust that fills the space between stars. These shockwaves compress the gas, often triggering the formation of new stars. This process, known as triggered star formation, is an essential part of galactic evolution. In a sense, supernovae are both the end and the beginning of the stellar life cycle. The death of a massive star in a supernova explosion often initiates the birth of new stars, ensuring that the process of stellar evolution continues in a galaxy. These new stars are often born in regions rich in the elements produced by previous generations of supernovae, meaning that they inherit the building blocks necessary for the creation of planets and, potentially, life. The interaction between supernovae and the interstellar medium creates a dynamic, ever-changing environment in galaxies, fostering cycles of destruction and creation that have been ongoing for billions of years. Galactic winds, which are powerful streams of gas ejected from galaxies, can also be driven by the energy released in supernova explosions. These winds carry material out of the galaxy and into the surrounding intergalactic medium. By studying these winds, astronomers gain insight into the feedback processes that regulate the growth of galaxies. Supernovae are a critical component of this feedback, as their explosive energy helps to drive the outflows that prevent galaxies from becoming too dense or forming too many stars too quickly. In dwarf galaxies, small, low-mass galaxies with fewer stars, supernovae play an even more pronounced role in shaping their evolution. Because these galaxies have weaker gravitational fields, the energy from supernova explosions can more easily push gas out of the galaxy. This removal of gas can suppress star formation, altering the long-term fate of the galaxy. Supernova feedback is thought to be one of the reasons why dwarf galaxies are often gas-poor and form stars at a much slower rate than larger galaxies like the Milky Way. Speaking of the Milky Way, our own galaxy has been shaped by countless supernovae over its 13.6 billion year history. Supernovae have influenced the formation of the spiral arms, where star formation is most active, and have played a role in regulating the growth of the galaxy's central bulge. Furthermore, supernova remnants, expanding shells of gas and dust left behind after an explosion, can be found scattered throughout the galaxy. These remnants are some of the most striking objects in the night sky, glowing brightly in X-rays and radio waves as they slowly dissipate over tens of thousands of years. One of the most famous supernova remnants is the Crab Nebula, located about 6,500 light-years from Earth. The Crab Nebula is the remnant of a supernova that was observed by Chinese and Middle Eastern astronomers in the year 1054. The explosion was so bright that it was visible in broad daylight for several weeks. Today, the Crab Nebula continues to expand, emitting radiation across the electromagnetic spectrum. At its center lies a rapidly rotating neutron star, the Crab Pulsar, which powers the nebula's emission and provides a stunning example of the connection between supernovae and neutron stars. The study of historical supernovae, like the one that created the Crab Nebula, offers valuable insights into the frequency of these events and their impact on Earth. Although supernovae are rare in any given galaxy, occurring roughly once every 50 years in a galaxy like the Milky Way, they leave lasting imprints that scientists can study for centuries. By examining the remains of past supernovae, astronomers can learn about the conditions that existed in our galaxy hundreds or even thousands of years ago. Supernovae may have also had direct impacts on Earth. There is evidence to suggest that nearby supernovae may have influenced Earth's climate and even contributed to mass extinctions. For example, when a supernova occurs within a few dozen light-years of Earth, it can release high-energy particles known as cosmic rays. These cosmic rays can penetrate Earth's atmosphere and potentially cause damage to the ozone layer, increasing the amount of harmful ultraviolet radiation that reaches the surface. Some scientists have hypothesized that past mass extinctions, such as the Ordovician-Silurian extinction event about 450 million years ago, may have been triggered by a nearby supernova. Additionally, there are tantalizing clues that supernovae may have deposited certain radioactive isotopes on Earth. In 1998, scientists discovered traces of the isotope iron-60 in deep-sea sediments. Iron-60 is produced in supernovae, and its presence on Earth suggests that a supernova explosion occurred relatively close to our solar system, within about 100 light-years, within the last few million years. Further studies have found iron-60 in lunar soil and in cosmic dust collected from the ocean floor, providing additional evidence of nearby supernova activity. While the possibility of a supernova affecting life on Earth is an intriguing scientific question, it is important to note that the chances of a supernova occurring close enough to cause significant harm in the near future are extremely low. The nearest star capable of going supernova, Betelgeuse, is about 640 light-years away, far enough that, while its explosion would be spectacular to observe, it would pose no threat to life on Earth. Betelgeuse, a red supergiant star in the constellation Orion, has garnered significant attention in recent years due to its unusual dimming behavior. Some astronomers speculated that this dimming could be a sign that Betelgeuse is nearing the end of its life and could soon explode as a supernova. However, recent studies suggest that the dimming was likely caused by dust ejected from the star's surface, rather than an imminent supernova. Still, the fate of Betelgeuse remains an open question, and when it eventually does explode, it will provide a front-row seat to one of the most spectacular events in the universe. The study of supernovae is also deeply intertwined with the search for extraterrestrial life. As we mentioned earlier, supernovae distribute the heavy elements necessary for the formation of planets and life. Without the contributions of supernovae, planets like Earth, with its rich array of elements such as carbon, oxygen, and nitrogen, would not exist. In this sense, supernovae are indirectly responsible for creating the conditions that allow life to thrive. However, supernovae also represent a potential threat to life, particularly if they occur too close to a planetary system. This delicate balance between creation and destruction underscores the complexity of the universe and the fine-tuned conditions that make life possible. Astrobiologists are particularly interested in how supernovae influence the habitability of planets in different regions of the galaxy. For example, planets located too close to the galactic center, where star formation and supernova activity are more frequent, may be exposed to higher levels of radiation, making them less hospitable to life. Conversely, planets located in the galactic outskirts may be too far from the heavy element-enriched regions needed for planet formation. This concept of a galactic habitable zone, a region of the galaxy where conditions are just right for the formation and maintenance of life, adds another layer of complexity to the search for extraterrestrial civilizations. Supernovae, in their dual role as creators and destroyers, play a central part in shaping the boundaries of this habitable zone. As humanity continues to explore the cosmos, the study of supernovae will remain a key focus of astronomical research. Supernovae are not just rare, catastrophic events, they are a fundamental part of the universe's ongoing evolution. Through their violent deaths, stars leave behind a legacy that spans the cosmos, influencing everything from the formation of new stars and planets to the structure of galaxies and the fate of the universe itself. In the coming decades, new technologies and observational techniques will allow astronomers to study supernovae in unprecedented detail. Space-based observatories like the James Webb Space Telescope and ground-based facilities like the Extremely Large Telescope, ELT, will offer new insights into the physics of supernova explosions and their role in cosmic evolution. At the same time, the continued study of gravitational waves will reveal more about the mysterious compact objects that supernovae leave behind. In the grand tapestry of the universe, supernovae are among the most awe-inspiring and consequential events. Their brilliance, though fleeting, illuminates the depths of space and time, offering a glimpse into the processes that govern the cosmos. As we strive to understand these cosmic explosions, we are also reminded of our own connection to the stars, our place in the universe, and the profound beauty of the forces that shape our existence. Supernovae, in their breathtaking explosions, are not only harbingers of destruction but also serve as powerful engines of cosmic transformation. They inject an extraordinary amount of energy into the surrounding space, reshaping the environment for millennia and giving rise to complex phenomena that help astronomers understand how galaxies and planetary systems evolve. While their spectacular visuals have captivated the human imagination for centuries, the scientific ramifications of these stellar events are even more profound. At the core of every supernova is the process of nucleosynthesis, a term that refers to the formation of elements heavier than hydrogen and helium. It is within the fiery core of a dying star that elements like carbon, oxygen, silicon, and iron are forged. These materials, which are necessary for the development of rocky planets and the emergence of life, do not exist in isolation. Rather, they are propelled outward into space by the cataclysmic explosion. Without supernovae, these heavy elements would remain trapped within stars, and the universe would be deprived of the building blocks necessary for the creation of complex chemistry and, ultimately, biology. The cycle of life and death for stars is, therefore, deeply intertwined with the evolution of planetary systems. When supernova remnants collide with clouds of gas and dust, the shockwaves compress the material, sparking the formation of new stars and planetary systems. This cycle ensures that every new generation of stars is richer in the elements necessary for planet formation and for sustaining life. In this way, supernovae are the universe's way of continually enriching its own material, laying the groundwork for future complexity. As astronomers peer deeper into the universe, they have discovered that supernovae are not uniform. There are different types of supernovae, each with its unique signature and cause. The two primary types are Type 1 and Type 2 supernovae, which are differentiated by the processes that lead to their explosions. Type 2 supernovae occur in massive stars that are at least 8 times the mass of our Sun. These stars undergo nuclear fusion in their cores, fusing lighter elements like hydrogen into heavier ones over millions of years. As the star exhausts its fuel, it no longer has the outward pressure to counterbalance the force of gravity. The core collapses, triggering a supernova explosion. In the aftermath of this explosion, what remains can either be a neutron star or, if the star was massive enough, a black hole. Type 1 supernovae, on the other hand, occur in binary star systems where one of the stars is a white dwarf. In this scenario, the white dwarf accretes material from its companion star until it reaches a critical mass, causing a runaway nuclear reaction that leads to a violent explosion. Unlike Type 2 supernovae, which leave behind a compact remnant, Type 1 supernovae often obliterate the white dwarf entirely, leaving only a glowing remnant of the explosion. Both types of supernovae are essential for understanding the broader dynamics of the cosmos. Type I supernovae, in particular, have become invaluable tools for measuring cosmic distances. Because they all explode with roughly the same intrinsic brightness, astronomers can use them as standard candles to gauge how far away distant galaxies are. This ability to measure distances across vast stretches of space has led to one of the most remarkable discoveries in modern cosmology: the accelerating expansion of the universe. In the late 1990s, astronomers studying distant Type I supernovae made the surprising discovery that these supernovae were dimmer, and therefore farther away, than expected. This indicated that the expansion of the universe was not slowing down, as had long been thought, but was actually speeding up. This discovery, for which the 2011 Nobel Prize in Physics was awarded, introduced the concept of dark energy, a mysterious force that permeates the universe and drives its accelerating expansion. To this day, dark energy remains one of the most significant unsolved mysteries in cosmology, and supernovae are at the heart of this groundbreaking discovery. But even as supernovae help unravel cosmic mysteries, they are also harbingers of mystery themselves. One of the most perplexing phenomena in astrophysics is the enigmatic gamma-ray burst, GRB. These bursts of high-energy gamma radiation, detected by satellites, are some of the most energetic events in the universe. Many GRBs are thought to be associated with supernovae, particularly those resulting from the collapse of massive stars into black holes. The link between supernovae and GRBs is still being studied, but it offers a tantalizing glimpse into the most extreme processes that occur in the universe. Supernovae also play a critical role in the evolution of black holes and neutron stars, which are among the most exotic objects in the cosmos. As previously mentioned, when a massive star undergoes a supernova explosion, it can leave behind a neutron star, a superdense remnant composed almost entirely of neutrons. These stars are only about 20 kilometers across but contain more mass than the Sun. Neutron stars often exhibit extreme behavior, such as rapidly spinning and emitting beams of radiation, which we observe as pulsars. In binary systems, neutron stars can also merge with each other or with black holes, producing gravitational waves that ripple through spacetime and can be detected by observatories like LIGO and Virgo. Black holes, the densest objects in the universe, are also born from supernova explosions. When the core of a massive star collapses under its own gravity, it can form a black hole, an object with such a strong gravitational pull that not even light can escape it. The study of black holes and their formation is one of the most active areas of research in modern astrophysics, and supernovae are key to understanding how these enigmatic objects come into existence. On the cutting edge of supernova research is the study of parent stability supernovae, a type of supernova that occurs in stars that are more than 150 times the mass of the Sun. These stars are so massive that they undergo a process where the energy in their cores creates pairs of electrons and positrons, which reduces the pressure holding the star up against gravity. The result is a runaway collapse that leads to an explosion so powerful that the entire star is destroyed, leaving no remnant behind. Parent stability supernovae are thought to be incredibly rare, but they offer insights into the behavior of the most massive stars in the universe. Astronomers are also exploring the possibility of superluminous supernovae that are much brighter than typical ones. These events are still not fully understood, but they may be caused by a variety of mechanisms, including the formation of highly magnetized neutron stars known as magnet-ars or interactions between the supernova ejecta and surrounding gas. Superluminous supernovae are particularly intriguing because they are so bright that they can be seen at great distances, offering a window into the early universe when the first stars and galaxies were forming. As we look to the future, the study of supernovae is poised to enter a new era. With advancements in telescope technology, astronomers will soon be able to observe supernovae in unprecedented detail, from their initial outbursts to their long-term remnants. The James Webb Space Telescope, JWST, launched in 2021, is already revolutionizing our understanding of the early universe and will likely contribute to new discoveries about the role of supernovae in shaping galaxies and star systems. Ground-based observatories like the Vera C. Rubin Observatory, which is expected to begin operations in the coming years, will conduct large-scale sky surveys that could identify thousands of new supernovae, providing an unparalleled dataset for studying these cosmic explosions. Additionally, the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, has opened a new frontier in supernova research. By observing the gravitational waves produced by supernovae, scientists can gain direct insights into the dynamics of the core collapse that triggers the explosion. This new form of multi-messenger astronomy, which combines observations of light, gravitational waves, and particles like neutrinos, will provide a more complete picture of the physical processes at work in supernovae. In the grand scheme of things, supernovae are far more than just dazzling fireworks displays in the night sky. They are the engines of cosmic alchemy, creating the elements that make up planets, stars, and life itself. They are the architects of galaxies, shaping their structure and dynamics over billions of years. They are the sentinels of the universe, revealing its deepest mysteries through the light they emit, the particles they scatter, and the waves they generate. And perhaps most importantly, they remind us that we are connected to the cosmos in profound and fundamental ways. As we continue to explore the universe, the study of supernovae will undoubtedly lead to new discoveries that challenge our understanding of the cosmos and our place within it. From the birth of stars to the creation of black holes, supernovae are at the heart of some of the most important processes in astrophysics. Their light, traveling across vast distances, tells the story of the universe itself, a story of death and rebirth, of destruction and creation, of the infinite dance of matter and energy that has shaped the cosmos for billions of years and will continue to do so for billions more. In this grand narrative, supernovae are not merely spectacular explosions. They are the cosmic storytellers, illuminating the darkness of space with their brilliant light and the profound implications of their existence. Each supernova, in its final moments, tells a tale of the universe's past, present, and future, a tale that we are only just beginning to understand. The study of supernovae, with their profound impact on the universe, reveals a tapestry of cosmic phenomena that extends far beyond the boundaries of traditional astronomy. These explosive events serve as a focal point for understanding fundamental processes in astrophysics, cosmology, and even the search for extraterrestrial life. As we continue to probe deeper into the nature of supernovae, we uncover new insights that challenge our understanding of the universe and our place within it. One particularly intriguing aspect of supernova research is the concept of a supernova remnant, which is the expanding cloud of gas and dust left behind after the explosion. These remnants offer a unique window into the aftermath of a supernova and the processes that shape the evolution of the interstellar medium. By studying supernova remnants, scientists can investigate how the energy and material ejected by the explosion interact with the surrounding gas and dust, influencing the formation of new stars and planetary systems. Supernova remnants are often categorized based on their appearance and the physics involved. One well-known type is the shell type remnant, which forms a spherical shell of expanding gas and dust. Examples include the Crab Nebula and the remnants of the Tycho supernova. These remnants are characterized by their expanding, often circular shapes and the high-energy radiation they emit. The study of shell-type remnants provides valuable information about the dynamics of the explosion and the composition of the ejected material. Another type of supernova remnant is the pulsar wind nebula, which is associated with a rapidly rotating neutron star known as a pulsar. The Crab Nebula, mentioned earlier, is a classic example of a pulsar wind nebula. In these remnants, the pulsar's intense magnetic field and rapid rotation create a powerful wind of charged particles that interacts with the surrounding gas, producing intricate structures and high-energy emissions. Pulsar wind nebulae offer insights into the behavior of neutron stars and the mechanisms of particle acceleration in extreme environments. The study of supernova remnants also has practical applications in understanding the distribution of heavy elements throughout the galaxy. As supernovae eject their cores and outer layers into space, they contribute to the enrichment of the interstellar medium with elements like iron, silicon, and magnesium. These elements eventually find their way into new stars and planetary systems, influencing the chemical composition of future generations of celestial bodies. By analyzing the spectra of supernova remnants, scientists can trace the distribution of these elements and gain insights into the chemical evolution of galaxies over cosmic time scales. The interaction between supernova remnants and their surrounding environment can also produce fascinating phenomena like shock waves and bubbles. When the material from a supernova explosion collides with the interstellar medium, it creates shock waves that propagate outward from the site of the explosion. These shock waves compress and heat the surrounding gas, often triggering the formation of new stars and dense molecular clouds. The resulting bubbles of hot, ionized gas can be observed in various wavelengths, including X-rays and radio waves, providing valuable information about the dynamics of the explosion and the subsequent star formation. In addition to their impact on the interstellar medium, supernovae also play a crucial role in the larger-scale structure of the universe. The distribution of supernovae across different types of galaxies, spiral, elliptical, and irregular, can provide insights into the history of star formation and the evolution of galactic structures. For example, the rate of supernovae in a galaxy can indicate the intensity of star formation, with more frequent supernovae suggesting a higher rate of star birth. This information helps astronomers understand the processes that drive galactic evolution and the formation of large-scale structures like galaxy clusters. The study of supernovae also has implications for our understanding of the universe's expansion. As mentioned earlier, Type I supernovae have been used to measure cosmic distances and reveal the accelerating expansion of the universe. This discovery has led to the development of the concept of dark energy, a mysterious force that drives the universe's acceleration. By studying supernovae in different epochs of cosmic history, astronomers can probe the properties of dark energy and its effects on the universe's expansion. The quest to understand supernovae also intersects with the search for extraterrestrial life. The synthesis of heavy elements in supernovae and their subsequent distribution throughout the galaxy play a critical role in the formation of planets and the development of life. By examining the chemical composition of distant exoplanets and their atmospheres, scientists can assess their potential habitability and the likelihood of life. Supernovae, in this context, are both creators and destroyers, shaping the environments where life may arise and influencing the potential for extraterrestrial civilizations. In the realm of theoretical astrophysics, supernovae offer a testing ground for various models of stellar evolution and cosmic phenomena. The complex interplay between gravity, nuclear physics, and radiation in a supernova explosion challenges our understanding of fundamental physics. Researchers use supernovae as natural laboratories to test and refine models of stellar interiors, explosive nucleosynthesis, and the behavior of matter under extreme conditions. These models help us decipher the mechanisms behind supernovae and their impact on the universe. The study of supernovae also inspires future missions and observational campaigns. Upcoming space telescopes and observatories, such as the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope, will provide unprecedented views of supernovae and their remnants. These missions will enhance our ability to observe distant supernovae, measure their properties, and explore their role in cosmic evolution. Supernovae are not just cosmic spectacles but fundamental drivers of the universe's dynamics. They are the engines of cosmic recycling, the architects of stellar systems, and the beacons that illuminate the universe's past and future. By continuing to study these explosive events, we deepen our understanding of the cosmos and our place within it. The mysteries of supernovae remind us of the grandeur and complexity of the universe, inspiring awe and curiosity as we explore the far reaches of space and time. As we gaze into the night sky and witness the remnants of supernovae scattered across the universe, we are reminded of our connection to the stars and the cosmic forces that shape our existence. The light from a distant supernova carries with it a story of creation, destruction, and rebirth, a story that spans billions of years and encompasses the full spectrum of cosmic phenomena. In unraveling this story, we uncover the profound truths about the universe and our place in the grand tapestry of existence. Supernovae are not merely celestial fireworks. They are the cosmic architects, the celestial storytellers, and the harbingers of change. Through their explosive beauty and profound impact, they reveal the dynamic and interconnected nature of the universe, inviting us to explore the wonders of the cosmos and to embrace the mysteries that lie beyond the stars. Supernovae, as cosmic phenomena, not only reshape their local environments but also influence broader aspects of cosmic evolution. Their role in the universe is a testament to the interconnectedness of celestial events, illustrating how the life cycles of stars, the formation of galaxies, and the very fabric of spacetime are intricately linked. One area of active research related to supernovae is their influence on the formation and evolution of galaxies. When a supernova occurs, it injects substantial energy into the interstellar medium, creating shock waves that can compress nearby gas clouds. This compression can trigger the collapse of these clouds, leading to the formation of new stars and star clusters. Consequently, supernovae play a pivotal role in regulating star formation rates within galaxies. In this way, supernovae act as cosmic feedback mechanisms, balancing the growth of galaxies and influencing their overall structure. Furthermore, the energy and material ejected by supernovae contribute to the galactic chemical enrichment process. Over time, the cumulative effects of countless supernovae have infused galaxies with a diverse array of heavy elements, which are essential for the formation of planets and life. By analyzing the composition of distant galaxies and their stellar populations, astronomers can trace the history of supernovae and gain insights into the chemical evolution of the universe. The study of supernovae also intersects with the field of gravitational wave astronomy. Gravitational waves, Ripples in the fabric of space-time caused by the acceleration of massive objects were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Since then, gravitational wave observatories have detected several events associated with supernovae, including the mergers of neutron stars and black holes. These observations have provided new insights into the dynamics of supernova explosions and the formation of compact remnants. One particularly fascinating area of research is the study of electromagnetic counterparts to gravitational wave events. When a neutron star merger or black hole merger occurs, it can produce a range of electromagnetic signals, including gamma-ray bursts, optical emissions, and X-rays. By correlating gravitational wave detections with observations of these electromagnetic counterparts, scientists can gain a more comprehensive understanding of the processes occurring during and after a supernova explosion. The study of supernovae also has implications for understanding the origins of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Supernova explosions are thought to be one of the primary sources of cosmic rays, as the shock waves generated by the explosion accelerate particles to extreme energies. By studying supernova remnants and their associated cosmic rays, scientists can learn more about the mechanisms of particle acceleration and the distribution of cosmic rays throughout the galaxy. In addition to their impact on the universe's physical processes, supernovae also have a cultural and historical significance. For centuries, supernovae have been observed and recorded by various civilizations, often serving as celestial omens or symbols of change. Historical records of supernovae, such as the famous supernova observed by Chinese astronomers in 1054 AD, which created the Crab Nebula, provide valuable information about the historical frequency and distribution of supernovae. These records also offer insights into how ancient cultures interpreted and understood these cosmic events. As technology advances, astronomers are developing new techniques to study supernovae with greater precision. One such technique is time domain astronomy, which focuses on observing and analyzing transient astronomical events, including supernovae, in real time. By monitoring the sky for sudden changes in brightness, astronomers can capture the early phases of supernova explosions and study their evolution over time. This approach has led to the discovery of numerous new supernovae and has provided valuable data for understanding the diversity of supernovae and their progenitor stars. Another exciting development is the use of machine learning and artificial intelligence in supernova research. By applying advanced algorithms to large datasets from surveys and simulations, scientists can identify patterns and anomalies that may be missed by traditional methods. Machine learning techniques have been used to automate the detection of supernovae, classify their types, and predict their properties. These tools are transforming the way supernovae are studied and analyzed, enabling researchers to process vast amounts of data more efficiently. The study of supernovae is also expanding to include observations in various wavelengths beyond visible light. For example, radio telescopes can detect the emission from supernova remnants and the interaction of supernovae with their environment. X-ray observatories, such as the Chandra X-ray Observatory, provide detailed images of the high-energy emissions from supernova remnants, revealing the complex structures and processes occurring in these regions. Observations in multiple wavelengths offer a more complete picture of supernovae and their effects on the surrounding space. In summary, supernovae are more than just spectacular explosions in the night sky. They are fundamental events that shape the universe in profound ways. They drive the chemical evolution of galaxies, influence the formation of new stars and planetary systems, and provide insights into the most extreme conditions in the cosmos. Through their interactions with the interstellar medium, their impact on cosmic structures, and their role in producing gravitational waves and cosmic rays, supernovae offer a wealth of information about the nature of the universe and its underlying processes. As we continue to explore the mysteries of supernovae, we gain a deeper understanding of the universe and our place within it. The study of these cosmic explosions not only enriches our knowledge of astrophysics, but also inspires us to contemplate the grandeur and complexity of the cosmos. Supernovae are a testament to the dynamic and interconnected nature of the universe, reminding us of the beauty and significance of the celestial forces that shape our world. As we delve deeper into the study of supernovae, it becomes clear that their significance extends far beyond the immediate explosion and remnant phases. The implications of supernovae touch on fundamental questions about the universe's structure, the life cycles of celestial objects, and even the origins of cosmic phenomena that influence our everyday lives. One of the most intriguing aspects of supernovae research is their connection to the broader cosmic web. The cosmic web is the large-scale structure of the universe, consisting of vast filaments of dark matter and gas that connect clusters of galaxies. Supernovae contribute to this web by influencing the distribution and movement of intergalactic gas. The shock waves from supernovae can propagate through these cosmic filaments, affecting the density and temperature of the gas within them. This, in turn, influences the formation and evolution of galaxies and galaxy clusters. Understanding the role of supernovae in shaping the cosmic web is essential for comprehending the large-scale structure of the universe and the processes that govern its evolution. Additionally, supernovae play a crucial role in the formation of complex molecules and the potential for life elsewhere in the universe. The heavy elements produced by supernovae, such as carbon, nitrogen, and oxygen, are the building blocks of organic molecules essential for life. These elements are dispersed into space and incorporated into new star systems and planetary bodies. By studying the chemical composition of supernova remnants and the surrounding interstellar medium, scientists can gain insights into the distribution of life-essential elements and the conditions that might support the emergence of life on other planets. The role of supernovae in galactic chemistry and star formation also extends to understanding the origin of cosmic dust. Cosmic dust, composed of tiny particles of carbon, silicates, and other materials, plays a vital role in the formation of stars and planetary systems. Supernovae contribute to the creation of this dust by producing and dispersing a variety of elements into space. The study of supernovae and their remnants provides valuable information about the origins and distribution of cosmic dust, which in turn helps us understand the processes that lead to the formation of planets and the potential for habitable environments. Supernovae also offer important clues about the nature of dark matter, an elusive substance that makes up a significant portion of the universe's mass but does not emit, absorb, or reflect light. The impact of supernovae on their surroundings and their interaction with dark matter can provide indirect evidence about the properties and distribution of dark matter. For example, the way supernova remnants expand and interact with dark matter halos can offer insights into the distribution of dark matter in galaxies and galaxy clusters. This research helps to refine our understanding of dark matter and its role in the universe's structure. Furthermore, the study of supernovae has implications for our understanding of cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. Supernovae are believed to be one of the primary sources of cosmic rays, as the shock waves from the explosion accelerate particles to extremely high energies. By examining the remnants of supernovae and the cosmic rays they produce, scientists can gain insights into the mechanisms of particle acceleration and the behavior of cosmic rays as they traverse the galaxy. Another fascinating area of research is the study of supernovae in the context of multi-messenger astronomy. Multi-messenger astronomy involves the simultaneous observation of cosmic events using different types of messengers, such as light, gravitational waves, neutrinos, and cosmic rays. Supernovae are ideal candidates for multi-messenger studies because they produce a wide range of signals across the electromagnetic spectrum and can also generate gravitational waves and neutrinos. By combining data from different observatories and detectors, scientists can obtain a more comprehensive understanding of the physical processes involved in supernovae and their impact on the universe. One of the challenges in supernova research is the difficulty of observing these events in their early stages. Supernovae are often discovered only after they have reached their peak brightness, making it challenging to study their initial conditions and evolution. However, advancements in astronomical surveys and observational techniques are improving our ability to detect and monitor supernovae in real time. For example, transient surveys that scan the sky for sudden changes in brightness are helping to identify new supernovae and track their evolution from the moment they first appear. This real-time data is crucial for understanding the dynamics of supernovae and their role in the cosmos. The study of supernovae also intersects with the field of theoretical astrophysics, where researchers develop and test models to explain the observed phenomena. These models include simulations of supernova explosions, the formation of neutron stars and black holes, and the interactions between supernovae and their environment. By comparing theoretical predictions with observational data, scientists can refine their understanding of the underlying physics and improve their models of stellar evolution and supernova dynamics. Moreover, supernovae are a key area of research for understanding the origins of the universe. The light from distant supernovae provides valuable information about the early universe and the formation of the first galaxies and stars. By studying the light from supernovae that occurred billions of years ago, scientists can probe the conditions and processes that shaped the early universe and gain insights into the formation and evolution of cosmic structures. The impact of supernovae on our understanding of the universe extends to their potential for influencing future space exploration and technology. For example, the study of supernovae can inform the development of space missions and instruments designed to observe and analyze cosmic phenomena. Understanding the properties and behavior of supernovae can also aid in the design of experiments and technologies for detecting and studying high-energy particles, gravitational waves, and other astrophysical signals. In conclusion, supernovae are among the most dynamic and influential events in the universe. Their role in shaping galaxies, enriching the interstellar medium, and influencing the formation of planetary systems highlights their significance in cosmic evolution. The study of supernovae encompasses a wide range of scientific disciplines, from astrophysics and cosmology to particle physics and observational astronomy. As technology and observational techniques continue to advance, our understanding of supernovae will deepen, revealing new insights into the nature of the universe and our place within it. Supernovae are not merely spectacular explosions but fundamental events that drive the cosmic processes shaping our universe. They are the engines of stellar evolution, the architects of galactic structures, and the sources of the elements essential for life. Through their interactions with the cosmic environment and their impact on the broader universe, supernovae offer a profound glimpse into the interconnectedness of celestial phenomena and the grandeur of the cosmos. As we continue to explore the mysteries of supernovae, we embrace the opportunity to uncover the secrets of the universe and expand our understanding of the fundamental forces that govern the cosmos. As we delve even deeper into the study of supernovae, their significance extends into many facets of astrophysical research, intersecting with a broad range of cosmic phenomena and contributing to our understanding of fundamental processes in the universe. The exploration of supernovae not only illuminates their immediate effects but also offers insights into their broader implications for cosmic evolution, stellar life cycle, and the fundamental laws of physics. One of the most profound areas of research related to supernovae involves their role in the cosmic inventory of elements and isotopes. Supernovae are primary sites of nucleosynthesis, where the intense conditions during the explosion facilitate the creation of heavy elements that cannot be produced through regular stellar fusion processes. These elements, including iron, nickel, and various radioactive isotopes, are expelled into space and become part of the interstellar medium. Over time, this material contributes to the formation of new stars and planetary systems. By studying the composition of supernova remnants and the distribution of these elements in galaxies, astronomers can trace the history of element formation and understand how the chemical composition of the universe has evolved over cosmic time scales. The radioactive isotopes produced by supernovae, such as nickel-56 and cobalt-56, offer valuable tools for understanding the physics of the explosion and the subsequent evolution of the supernova remnant. These isotopes decay over time, emitting gamma rays that can be detected by space-based observatories. By analyzing the gamma ray emissions from supernovae, scientists can gain insights into the amount and distribution of radioactive elements produced, as well as the dynamics of the explosion. This research helps to refine models of supernova nucleosynthesis and provides a deeper understanding of the processes that govern stellar explosions. In addition to their role in element formation, Supernovae also play a crucial role in regulating the interstellar medium and influencing the formation of new stars and galaxies. The shock waves produced by supernovae compress the surrounding gas and dust, leading to the formation of dense molecular clouds that can trigger star formation. This process, known as supernova-triggered star formation, is a key mechanism for the birth of new stars and the development of star clusters. By studying the interaction between supernova remnants and the surrounding interstellar medium, astronomers can gain insights into the mechanisms of star formation and the role of supernovae in shaping the structure of galaxies. Supernovae also have implications for the study of dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter, which does not emit or interact with light, is thought to be distributed throughout galaxies and galaxy clusters, influencing their formation and dynamics. Supernovae provide indirect evidence about the distribution of dark matter by studying the effects of supernova explosions on their surroundings. For example, the way supernova remnants interact with dark matter halos can provide insights into the distribution and properties of dark matter in different cosmic environments. Similarly, the study of supernovae has implications for our understanding of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Type I supernovae, in particular, have been used as standard candles to measure cosmic distances and track the expansion rate of the universe. The discovery of the universe's accelerating expansion has led to the development of the concept of dark energy, which remains one of the most significant and unresolved questions in cosmology. By analyzing the light from distant supernovae and comparing it to theoretical models of dark energy, scientists can gain insights into the nature of this elusive force and its impact on the evolution of the universe. The study of supernovae is also intertwined with the investigation of other high-energy astrophysical phenomena, such as gamma-ray bursts, GRBs, and active galactic nuclei, AGN. Gamma-ray bursts, which are among the most energetic events in the universe, are thought to be associated with certain types of supernovae and the collapse of massive stars. By studying the connections between supernovae and GRBs, researchers can gain insights into the mechanisms of these explosive events and their impact on the surrounding environment. Similarly, active galactic nuclei, which are powered by supermassive black holes at the centers of galaxies, can exhibit dramatic changes in luminosity and emission associated with supernovae and other cosmic events. Supernovae also play a role in the field of exoplanetary science. The heavy elements produced by supernovae contribute to the formation of planetary systems, including the planets, moons, and other celestial bodies within them. By studying the distribution of these elements in exoplanetary systems, scientists can gain insights into the conditions that might support the development of life and the potential habitability of distant worlds. Supernovae, therefore, have implications for the search for extraterrestrial life and the study of planetary environments beyond our solar system. The quest to understand supernovae also drives technological advancements in observational astronomy. The development of new telescopes, detectors, and analytical techniques has revolutionized our ability to study supernovae and their remnants. For example, advancements in high-resolution spectroscopy and imaging have provided detailed views of supernova explosions and their aftermath, allowing scientists to analyze the composition, velocity, and structure of supernova remnants with unprecedented precision. Similarly, the deployment of space-based observatories has enabled the observation of supernovae in various wavelengths, including X-rays, gamma rays, and infrared light, providing a more comprehensive understanding of these cosmic events. As we look to the future, the study of supernovae will continue to evolve with advancements in technology and observational techniques. Upcoming missions and observatories, such as the upcoming Nancy Grace Roman Space Telescope, the European Space Agency's Euclid mission, and the next-generation ground-based telescopes, will offer new opportunities for exploring supernovae and their role in the universe. These missions will enhance our ability to detect and monitor supernovae in real time, study their interactions with the cosmic environment, and gain insights into their impact on the formation and evolution of galaxies. In conclusion, supernovae are fundamental cosmic events that shape the universe in profound ways. They drive the chemical enrichment of galaxies, influence the formation of new stars and planetary systems, and provide insights into the fundamental forces and processes governing the cosmos. The study of supernovae intersects with a wide range of scientific disciplines, from astrophysics and cosmology to particle physics and observational astronomy. As we continue to explore the mysteries of supernovae, we uncover new insights into the nature of the universe and our place within it. Supernovae are not merely celestial phenomena. They are key to understanding the dynamic and interconnected nature of the cosmos, inspiring awe and curiosity as we unravel the secrets of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video if you found this video helpful and subscribe to the channel for more such amazing videos.